Hello. Right. For those of you who don't know me, I'm Sean. I'm a PhD student here. I should probably add a disclaimer in. This isn't actually part of my research at all. I'm doing sort of forensics type stuff, but this was from my masters. So I just read a lot about it, and I thought I'd and tell people about it if you're not aware of it. So can I get a quick show of hands who knows stuff about forensics in advance, so I know how to pitch it? Experts. So, I don't know, that's what, a third of people? That's not too bad. Okay, so I'm just going to go through a quick sort of overview. It's not going to be super detailed, maybe take half an hour or something like that to go through. Can everyone hear me, by the way? Yeah? Bit louder? Okay. So I'll start off, I'll talk briefly about hard disks. If you're not familiar with them, then just briefly compare it with NAND flash media, SSDs, that kind of thing. I'll talk about how NAND is actually implemented in practice, some of the algorithms that run on these things to actually make them viable in practice. I'll talk a tiny bit, it's like 1 or 2 slides, about managed versus unmanaged, and I'll sort of enumerate what types of flash are what and where they're used. Then I'll just talk about forensics concerns and some of the key literature in the area, which doesn't seem to have changed much in the last 5 years. So, I mean, if you've never seen a hard disk, you're probably in the wrong place, but it's just essentially a magnetic mechanical device, spinning platters. You can see here, the read heads on top. So the idea is you've got a big metal chunk that spins around on a spindle. It's broken up in a particular way. So these concentric circles are tracks. So that's where the actual data lies on the track. So the read head moves up and down these tracks in order to read the data. And this is one single platter, but the image you saw, where it had multiple going down like this, it would have a read head for each of the platters. So you'd have each of this layout on each one. So track is one concentric circle, but you've also got the notion of a cylinder, which is the same idea, but sort of in 3 dimensions. So if your read head's here, then it reads the entire cylinder at once. So tracks, the orange reddish part here. The bit that's highlighted, the sort of pi wedge, it's just sort of an arc cut along the circumference, 2 lines going out. That's your geometrical sector, which doesn't really mean anything except the intersection between this and this is the actual sector. So whenever you hear someone talk about this sector, they're talking about this sort of arc on one of the concentric circles. It's just a little line going around. And that's essentially where all the data is stored. That's the bit where the read head actually reads and writes to. And typically this was about 512 bytes until, I don't know, 5-10 years ago maybe, when hard disk sizes started to explode and we suddenly came up with 1, 2, 3, 8 terabyte drives. So in order to counter this, they had to increase the sector size a little bit. So they're now more commonly 4K, and I think 2K didn't really last very long. So they're quite high density now. Cluster, which I haven't talked about yet, is a file system construct. So a cluster is made up of 1 or more sectors. So you might have 1, 2, 3, 4. And that is the smallest allocation unit. So on NTFS, which is the Windows file system, it doesn't write to individual sectors. You get a cluster or a run of clusters, and you say, I want to write stuff to this cluster. And that's the green bit here, just showing that it's more than one. And I probably shouldn't touch that, because I'll start drawing all over it. The addressing is what, it used to be something called cylinder head sector, because we actually have physical devices, we've got cylinders, we've got heads, we've got sectors, it makes sense. All you need is a unique descriptor of where it is on the disk. But that has its limitations, and you only get to a certain size, a certain maximum sector count if you do it that way. And the old BIOSes sort of had these numbers hardwired, so you couldn't go beyond 256 bits or whatever. Nope, went too far. So these days we use what's called logical block addressing. And this just looks at sectors. So an individual sector has an individual address, and it's just a sort of one-to-one mapping, as it were. One handy thing about magnetic media is you can do overwrite in place. So if you've got one sector and it's filled with ones, and I want to go back and say, I don't want ones here anymore, I want zeros, or I want twos, or whatever layer of abstraction you're working at, it can just go back and write over in place. You don't have to do anything fancy, you just rewrite the data as it is in the exact same place on the disk. So that's just a quick sort of overview. I'm going to talk briefly about, well, I'll compare them all throughout, but NAND is where we're going to go now. So as you can see, there's no mechanical device here. There's no spinning plateaus, no big metal chunks. It's more or less a motherboard, a PCB with some flash module stuck to it. It's just all electronics. And you pull it off and you get a ball grid array or something similar. You've probably seen these around. So non-mechanical components, they're actually more or less the actual storage unit, flash, it's called a cell. So it's essentially just a transistor, and it basically resembles a NAND gate if you've ever done logic gates. You put in a 1 and 1, you get 1 out, you put 1 and 0, you get 0. So both bits have to be 1 to get 1 out. But if you've ever seen transistor diagrams as well, you'll probably notice the source, drain, gate, that sort of thing. So the idea is it's basically a transistor, but with an extra little bit added where you can actually store some information via a charge, and that's the floating gate part. That's not entirely important, but what is that it's non-volatile. So you turn your system off, you bring it back up, the data's still there. It doesn't disappear like system memory. Each cell can store 1, 2, or 3 bits, maybe more in the future with your vertical NAND stuff, which I won't really talk about. But the idea is that's the smallest unit. You want one single bit. But that isn't the actual thing we're operating on. That's just really low down. The actual thing we're really talking about is a page. So it's the smallest unit of allocation in NAND flash is a page, which is made up of many cells. So we've got our little cell down here, our NAND type transistor, put them all together into some arrangement. I think I've written down how many? No, I haven't written down how many pages, how many cells per page, but it changes depending on era, how old the disk is. It'll go up much like the sector count does. So each page is just composed of X number of cells and a bunch of out-of-band stuff. So we've got, say, 1 megabyte of data, but we've also got a little bit of bookkeeping, as it were. So your error correction stuff. So occasionally you'll read back a bit and you'll get an error. You want to correct it, there's some extra stuff that does that, some extra mechanisms for that. And this out-of-band area is actually used a bit differently by some of the flash-aware file systems, which I'll touch on a bit later. But so you can think of a page as essentially the sector of a solid-state drive. It's the smallest thing you can write to and the smallest thing you can read from. Okay, so pages are arranged into blocks. And blocks are only really interesting because they're the smallest erase unit. So in a hard disk, you can read, write, overwrite, delete, anything on a sector. You just do whatever you like with it. On NAND flash, you can read to a page, but if you want to erase stuff, you have to do it at the block level. And that only really matters because we can't overwrite in place. If I write to this page, I can't write to it again until I clear this entire block. So if I want to modify the data here, say I write a bunch of Fs, I want to change them to a bunch of Ds, I have to write it here instead of there and then mark the old one as unused now. So that's the major difference is you can't just replace stuff. You have to do a lot of mucking about behind the scenes to get it to work. And one key thing to remember is that when you're erasing a block, so when you're erasing all these pages, you're actually damaging the media itself. So each block only has a limited lifetime. You can erase it hundreds of thousands of times perhaps before it gives up and dies. Okay, so because you can't write in place, we have to come up with this weird sort of mapping. So we no longer have this logical block address mapping where we've got physical sector 1 is always logical block 1. We now have to say, okay, well, physical page or physical block 1 now might be mapped to logical block 3, 4, 5, 6, 7, 8. It's dynamic. I've got an illustration here, which is from a random web page that I found. So we write a bunch of stuff to physical 0, say that's, just get a physical page number, doesn't really matter. So say this is the first page on the entire SSD. We write some stuff in there, but we want to update that sector, that logical block address, so logical block 8000. We want to go back and say, okay, that's no longer Fs, that's zeros or Ds or 1s. So we go back and say, we tell the file system, write to this location. Behind the scenes, it says, okay, I can't write to this address again, I'll have to put it here. And we'll just sort of cross that out and deal with it later. And then again, if I want to go back and overwrite it again with zeros, I have to write it to a new location. So the flash translation layer is the thing that handles all this mapping. It's just a sort of abstract concept where you're doing this mapping behind the scenes, and You don't know about it when you're using the device. It just happens either in the flash controller or in the file system OS level, depending on whether it's managed or not. That's more or less it. But the only problem is you end up with a bunch of these points which would have at some point pointed to the same logical block address. So these are all address 8000 at some point, but these two aren't really used anymore. Does everyone follow what I mean by this? Okay. By the way, if you've got any questions, just stick up your hand. I'm quite happy to be interrupted. Well, saying interrupted makes it sound bad, but feel free to ask anything. So because we've got all these pages, all these copies or all these unused pages that are just floating about, we have to clean them up. Because if we just keep writing a new page every time, we'll eventually run out of pages. So maybe we've written the same file over and over and over a million times, the SSD's filled up with a bunch of garbage, and we only have one file that's actually in use. So this is called garbage collection. When we actually go back through this, it's sort of like memory garbage collection in that we've got a bunch of unused pointers and we go and clear them out of memory so that it can be used for other things. So what essentially happens is once a block is filled up with all these pages, we no longer need to erase it, and that frees it up for later allocation, and then the translation table can then point stuff in that direction. The problem with that is the NAND flash itself doesn't actually know about your files, it doesn't know about your logical block addresses as such. It only just says, I've got a page, I've got a block, I've got some addresses, tell me what to put there. So it doesn't really know when you've deleted the file, because the file system just says, mark this byte as a 1 or 0, delete this. In FAT32, it's like a lowercase sigma gets overwritten into the first part of the file name. So one solution, some of the initial SSDs, like the early Intel SSDs, implemented was to actually look at the file system. So if we put NTFS on the SSD, the actual flash controller would go and look at this and it says, okay, I know what NTFS is, I know it's got this construct called a dollar bitmap, and that tells me all the blocks that are signed and deallocated and what I can use. And in FAT, it's got the same thing. The file allocation table is essentially another bitmap that tells you about all these sectors. So that's all well and good, but you have to know about the file system. If you don't support the file system, you don't know what to do with it. But if you do have a bit of this knowledge, you can do sort of proactive garbage collection and go out of your way, so you're not waiting until you need it. You're doing it as you go and keeping everything tidy. So a better solution, if it exists, would probably not to be file system dependent. I may want to put some new file system on there to test it out, or I've maybe got a logical volume and that complicates things. And basically, you don't want to be waiting on the SSD to do this. It doesn't have to have knowledge of everything. So can anyone think of the more recent way of solving this and clearing up pages? Magic. So the first one's about hacking, but you've probably heard of this as soon as I say it. Trim. So it was in the media a fair bit when it came out because it solves a lot of problems. So what used to happen is you'd have an old SSD, it'd keep writing and writing and writing, and once all the spare pages had been used up, it would then have to execute an erase every time it went to write some new data. So your write performance went completely down the toilet. So when trim comes in, it's keeping on top of these pages all the time. It's being proactive about it. It's not waiting for all the pages to be used and then for you to write over something, which means it now knows that's free. It can just say, okay, the file system has told me that this particular page is no longer allocated. Logical blocks 0 through 1000 are now deallocated. I look at my flash translation table, I look at the pages, and I say, okay, I don't need these anymore. I'll mark them for garbage collection. Whenever the garbage collection runs, it goes and clears them out. And the garbage collection itself actually, it completely depends on the flash controller in place. It might do it really frequently, it might only do it when it needs to, and that sort of mucks up forensics a little bit as well. But this is a basic diagram just saying when you write stuff, you can say invalidate this data. So we've now got a block that has a few bad pages in it, and you can either move them out, you can move the good pages out. So say we had another 2 bad blocks here. So we get 4 bad blocks, 2 good blocks, and 2 unused. We could maybe move this stuff out and then erase the block, or just wait until it fills up with bad blocks. But either way, we know we have a good map of what's used and what isn't. And it also mitigates this thing called write amplification. Write amplification involves all this moving about of stuff in the background. So garbage collection, if it's moving things about in order to erase a block, it will essentially write the same page multiple times, even though it doesn't need to. But all of this incurs a lot of erases, incurs a lot of real wear on the device. And like I said, the individual blocks only have a certain finite lifetime. So the multi-layer stuff, where you're storing more than one bit, has a smaller lifetime than a single, like your SLC cells. So you might go from 100,000 to 10,000 if you're using the more cells, more bits per cell. So wear leveling tries to spread out these erases. So I'm no longer just saying, okay, these are from file system files, I won't touch these. The rest of the disk is scratch space. I'll just keep erasing that. So this side has been erased 400 times, this side has been erased once. So for dynamic wear leveling, you just say, okay, I keep a list of how often these blocks have been erased, and I'll just take the one that's the freshest every time. So you're bringing the whole lifetime of the entire SSD, all NAND modules, down at the same time. So you don't get random pieces of it dying, and what happens is you reduce the available size. So my 200 gig SSD might be 150 because part of it's just died. For static, we've got system files and other things that just sort of sit about. They're not moved, they're not rewritten. Once you install the OS, a lot of the files just sit there and they don't get modified at all. So static just says, okay, we'll move that out to a highly worn block. This block has been written erased 400 times. So we'll move the OS stuff over there for a while. And that means that gets a break and we can erase other parts of the SSD. And hybrid just sort of divides up the disk and says, we'll do dynamic stuff on this side and we'll do static stuff on this side. Oh yeah, and they throw in some extra NAND. So if your SSD is 120 gig, you might have an extra 8 gigabytes of actual NAND flash in there to facilitate this kind of juggling around in the background. And the amount of spare flash depends on the device. It'll be completely manufacturer dependent, device dependent, but typically you'll find the stuff suited for servers or industrial applications will have more spare flash because they want to keep them as robust as possible. In the real world, drives are pretty good. The lifetime is really an issue with the earlier SSDs. These days you don't really have to worry about it very much. So the Samsung A40 Pro is quite recent, A40 Evo, I think the A50 Evo is out now, but the A40 was quite popular. So along the bottom is the only really thing you have to pay attention to. Terabytes written, so that's 2,400 terabytes, that's 2.4 petabytes. You're probably not going to get through that with normal use. If you're writing a lot of forensic images to it all the time, yeah, okay, you might eventually run out, but this experiment was carried out by the Tech Report, which is a sort of techie website, where they just thought, okay, we'll take a bunch of drives, we'll write to them constantly, 24/7, and see how long they last. And they lasted months and months and months. Some of the drives fell off a bit earlier, as you can see on the left-hand side here, maybe the cheaper ones. They got to only 80% of a petabyte before they died. Whereas the more expensive ones make it, twice, 3 times that. And the performance is quite consistent as well. Whereas if before we had trim and all these other really clever mechanics for dealing with this stuff, you would find the write performance would drop off and would be completely useless at the end. So I've mentioned briefly unmanaged flash and managed flash. The main difference is where all of this stuff happens. So I mentioned garbage collection, wear leveling, and a little bit of ECC. For unmanaged flash, this all happens at the file system / OS system, like the OS level. So your early Android devices, for example, would have run yet another flash file system too, and they would have exposed raw NAND to the device. And for Linux, you've got this thing called a memory technology device, which is a sort of block interface to these things. So the file system had to know, which means all of this ECC stuff, that out-of-band stuff I was talking about, was actually used by the file system. So it's sequence numbers to keep track of when this block was overwritten and which version of this block it is. So if I overwrite, or I try to overwrite and then I write a new block, it increments the sequence number. So this is number 3 instead of number 2, so we know we don't need number 2 anymore. Yep, that's what it. And for managed, no surprises, it just moves it into an actual hardware module. So instead of communicating with the flash and seeing all of this stuff exposed and having your file system be able to deal with it, you talk to it as if it's a block device. So you can treat it like a hard disk. Because the flash controller does all this stuff behind the scenes, you don't have to care about it. And the nice thing about this is you can use a normal file system. You can put your ext4 on it, you can put NTFS on it, FAT, HFS plus if you really feel like it. But the out-of-band area takes a hit because this is all just background management stuff. We don't need it anymore for the file system, so while it's present on the actual SSD, you'll basically never see it. Varying levels of performance and cleverness in devices. So raw flash is raw flash. Embedded systems will have it built into the PCB where you just have a raw flash module. Early Android devices had them like that. But basically everything else is managed. So your SD cards, your embedded multimedia cards in modern phones, your SSDs, USB flash drives, anything that uses NAND flash these days is probably going to be managed in some sense. The only difference is the aggressiveness of the garbage collection and the complexity of the wear leveling and all that sort of stuff. So the lower end devices, not as clever, not as high performance, that kind of thing. So this is where I talk about the forensics bit, but does anyone have any questions about any of the stuff I've talked about? Is it clear enough? So acquisition methods. I know not everyone put their hand up for forensics type stuff. So there are a couple of ways of doing this. Software reading is probably the most common and depicted by the top picture here. In essence, you've got a device, you plug it into a write blocker, SATA, IDE if you're using the older drives, and that blocks any commands which would modify the data on the disk. Because if I plug it in otherwise, I may accidentally create a file, or just by mounting the file system, I can change the metadata on it. So the write blocker stops all that and says, okay, only read from this device, don't write anything new to it. And that's still viable for SSDs. You plug it up in the same way as a normal hard disk, blocks the SATA write interface, you just dump it using DD FTK, which just does a software read that uses the SATA interface, and the flash controller says, here's some stuff, here you go. And you can either do a logical or physical acquisition where you're just looking at the file system level stuff, or you're trying to get lower level things like what's actually written on the pages themselves, what's for a hard disk, what would be on the sector level acquisition. So you can try that. It may not work very well, but you can try it. The second step down, you're looking at JTAG. So these boards have got debug modes. The idea is you're not just creating a board out of nowhere and chucking it at the consumer. You pre-program it and you load on the firmware for the flash controller. So it's got debug pins, and then you can set commands and say, okay, what's on this NAND flash module, what's on this one, and it gives you a bit more bare metal access. The third mode is chip off, where you literally pull the pins, pull the NAND modules off of the board and stick them in some kind of chip reader. So in this case, it's Ming the Merciless from Wei et al., which I'll talk about a bit later. But this is a custom FPGA where they just dunked it in, read the data off via the raw pins on the device. So you're getting the lowest possible level of access to the memory because there's nothing in the way. You literally just have the NAND flash itself. So for unmanaged, you get a lot more of the behind-the-scenes stuff going on. So if it's unmanaged and you do a physical or logical acquisition, you'll get something that looks like this. So this is a paper that talks about how one of the flash-aware file systems works. So you've got your big data chunk, and then at the side you've got the spare area, which is sort of ambiguous and used differently by different file systems and different flash controllers. But this is the stuff I was talking about. You've got IDs, you've got sequence numbers, you've got some error correction, and it sort of exposes a bit more. And at this level, you're probably also getting multiple copies of the same file as well, because the file system can see all this stuff. It's all made aware to the acquisition when you do it. So if you do your software read with your DD, your FTK imager, you'll see all this stuff and you'll be able to construct file histories for what hasn't been garbage collected at least. For managed, it's a bit complicated, mainly because the flash controller is the boss. That's in the way for all of your SATA reads. That'll just give you whatever it feels like. And behind the scenes, it's doing all sorts of weird stuff as well. So you've got multiple NAND modules, So it can stripe it across. It can say, okay, I want to write 2 bits. I'll write a 0 to there and a 1 to there. And then if you want to get the data back, you have to read from them simultaneously, much like if you had RAID 0 on your hard disks. It can also do compression, so it can save physical NAND space by having hardware level compression and decompression. So you write 100 megabytes, it's only using up 80 megabytes of NAND. It can also flip the bits depending on the architecture. All the ones may be zeros and all the zeros may be ones. And at the lowest level, it might actually be doing encryption as well. So it can be doing compression, but also encryption. And this actually makes it really easy to securely erase them, because you've got one block that says I'm the key. The flash controller looks at the key and decrypts all the blocks before it sends them across the SATA interface before any of your software sees it. And if you want to erase the device, you just say, I'll change this key. Same kind of thing works with full disk encryption on hard disks as well. And I'm fairly certain the 840 Evo series lets you do this. Otherwise, you could just trim and garbage collect the entire device, but there's no guarantee it will actually erase the blocks. So for managed NAND forensics, trim and garbage collection are a bit of a problem because they actively clear out the evidence. If something has been deallocated and you've told the device about it using trim, and it goes and gets garbage collected, and it comes and erases that block, that stuff's gone. Right? That's it. It's just the end of story. It's gone. But if it's still there, so we have the case where we haven't erased the block, but it still has some pages in it which have been marked or trimmed for erasure. So there might be a bunch of data on there. So what happens when we ask the flash controller about it? Well, it turns out there's three rough categories of trim. So we've got the ones where we know what we're going to get back. If the device has trimmed that page or that block, we always get the same thing back. We either get ones, we get zeros, we get some predetermined pattern, but we don't get the original data. And we've also got undeterministic or non-deterministic, where you don't really know what you get back. You can do the same request across different periods of time and you'll get different stuff back. So again, you're at the mercy of the flash controller if you're doing stuff over the SATA interface. Which really means, any given device will behave differently from any other, and they probably all converge in just saying, yeah, you know what, this has been trimmed, you shouldn't care about it, we won't give you anything back. Over provisioning, so if you've got this extra 6, 8, 10, 20% of extra NAND, and you're asking the SATA controller, you're asking via the SATA controller to the flash controller, say, give me what you've got. It doesn't talk about that because that's outside the scope of what you're talking about. You think the disk is 200 gig, right? You can't even tell that other stuff's there. So there may be data on there, which again, hasn't been erased, but gets put in and out of use, as it were, by the behind the scenes. Slack space, so this is a concept mainly for hard drives. So we've got these sectors and we've got these clusters, but if I write a 1 kilobyte file and the cluster is 2 kilobytes, I've got all this space that hasn't actually been used. And that's sector slack, as it were. You've got different levels of slack, but that's the basic one. You don't really have that with NAND flash because you don't have sectors. There's no write in place. All you really have is what I've been talking about, the deallocated pages, which are still kicking about on a block. So if the block hasn't been erased, your slack is the pages that are left over. Because once the page has been erased and you only use 10% of the page, the rest of it is still zeroed out from the last erasure, because otherwise you wouldn't be able to write to it. The data remnants from trim and the aggressiveness of the garbage collection completely dependent on the manufacturer. So the early Intel stuff was really aggressive, but they might have toned that back due to other factors. But you never know. It's just when you do this, you have to really test your device ahead of time. And if you do end up saying, okay, let's just get rid of the flash controller, it's a nuisance, we'll physically pull the pins off, pull the NAND flash off the board. Hopefully we don't break it, hopefully we don't break all the ball grid arrays. And even if you do, you can resolder it. And we'll put it in an FPGA or some other chip reader / programmer. You still have all this other stuff on the previous page to contend with. Plus, you don't necessarily know what order the NAND modules were in. So you've got not only a fragmented file system, but you've got the individual pages being distributed across the entire space of memory. So you're not just dealing with, okay, we've got a bit of the JPEG here and a bit of the JPEG here. You've got individual pages for the JPEG scattered everywhere. They don't have to be next to each other at all. So yeah, that's fun. Okay, so I've got three papers I'll talk about. They're sort of the core SSD type papers. I had a quick look before I put the slides together to see if there's anything new. There's not an awful lot of anything happened. It just seems to be more or less the same. So I mentioned trim. Back in the old days, hard disk forensics, if you opened your hex editor and you saw that, it meant one of two things. Your hard disk hadn't been used, or someone has intentionally gone through and erased everything, or your file just happens to contain a bunch of zeros for some reason. But on an SSD, this can just happen because things have been trimmed, have been garbage collected, or the controller is saying, I'm going to clear that, I'll just give you zeros. So this is quite common, even if the disk is quite heavily utilized. So these guys were looking at trim from a forensics destructive point of view. Sort of an unintentional counter forensics, because the initial argument was, if you see this, they're not trying to hide stuff, this is just a behavior. So they took 15 SSDs, only 6 of them had trim support at the time because it was still quite new. Windows XP, Windows 7 and Ubuntu. Windows XP doesn't support trim. Windows 7 does, and I can't remember if the version of Ubuntu they were using does, but it certainly does now. They had these 3 capacity scenarios. So they had a fresh drive, they had a drive which was quite heavily used, so it had a lot of the space taken up, and they had one that hadn't very many files put on it yet. And the idea was, write a big file, write a small file, and then delete them and see what happens. So on a hard disk, you delete it, you go and mark the file system and say, we're not using that anymore, and if you don't do anything else, you're guaranteed to get that back. If you then go and start writing stuff to the disk, you might overwrite it, but more or less it should still be sitting about. But on an SSD, when you get trim enabled, as soon as you delete that, you're basically just waiting on the garbage collection to come along and break that for you. So, as I was saying with the early Intel stuff, the garbage collection was really aggressive. So when they performed this experiment, simply deleting these things and waiting a little bit gave you 0% recovery. Because as soon as the controller saw that that stuff was trimmed, it went and raised it and got rid of it straight away. Other configurations that supported trim, a bit more lax. 20 to 30% recovery. Not really sure how long they waited to do that. But obviously this is a fairly static scenario. If you delete something and then reboot and then you go and read it again, you haven't really done much to the disk. So 20 to 30% is you just saying delete the file. But if you've deleted it and then you've gone and done a bunch of other stuff, then you come back, the garbage collection might have run because the disk is actually being used. So their methodology is a bit flaky, but it's a good demonstration of how you can unintentionally wipe parts of your disk.
What did they use for acquisition and analysis?
They're not right on here. Yeah, software read. So they were just doing like your typical DD over your SAP interface. And again, that would also depend on what the trim controller, the flash controller was giving you for trim data at the time. So that you might do the exact same experiment now and find that even if it hasn't been garbage collected, it still gives you zeros. But that's part of the problem with these early papers, is they're using kind of outdated stuff. But
So I was wondering if it just gave you zeros anyway,
yeah.
and interpret those.
But I think the main, if you take anything away from this talk, it's that the flash controller does what it likes, and you have to put up with that. So Automagic evidence destruction with some fire and brimstone and all sorts of magic happening. The basic idea of this was to test the difference between hard disk and SSD data corrosion if you don't do anything really. So they filled the device with strings with uppercase evidence, so you can imagine how many of them were kicking about on a several gigabyte disk. Then the idea was you quick format the disk, you shut it down and you boot it up, and then you start sampling the disk to see what happens. And they were recovering it again via software means. So unsurprisingly, the hard disk doesn't really destroy much of the data at all. When you reformat, all you're really doing is writing over some of the core file system stuff. The actual data itself should be largely untouched because there's no reason to go back through and erase everything. You're not putting zeros over the entire disk because there's no need. So you boot up and you find, okay, 99.99% of hard disk data is still there after a quick format because it's not supposed to wipe data. But on an SSD, they had this sampling algorithm running. They could actually see the data disappear off the disk as they were looking at it. So I think it was within 160 seconds most of these garbage collection routines kicked in. And I think by the 3-minute mark, basically all the data was, 90% of the stuff was dead. And again, this is them not even using the disk, this is just it sitting there working away on its own. And they thought, okay, this is kind of horrible for a forensics point of view. I get to a suspect, he's got a locked door, he quick formats his drive and turns it off, and that's it, everything's gone. So they thought, okay, maybe we can mitigate this slightly, we'll put a write blocker in the way, that prevents disks from writing to themselves. You can't change it that way. Doesn't do any good. And the reason being, it's all happening at the flash controller level, which isn't really impacted by the SATA bus at all, because it's doing this regardless of whether or not. Yeah.
Power does the controller use on its own?
What power?
Well, is it using your battery or just wonder what impact
It's just
that
however you're.
has constantly doing its own thing?
Oh yeah, I mean for.
Or is it just negligible amounts?
I think it's enough to notice it. So the Keysight guy was actually saying for modern mobiles, if they're not plugged in, the garbage collection will maybe weight off a bit. And once you're plugged in, you can then do whatever you like because you have infinite power. But I think it actually does spike up enough to actually matter. So you might find if you're running on a laptop battery that it doesn't do it for power consumption reasons. But if you're plugged into a PC, there's no reason. Yeah.
Is there a way to power off the garbage collection, like hack the?
You could probably hack the firmware, but by the time you've done that, it's probably already toasted the evidence. Unless you know ahead of time, you're going to need to acquire the device before anything bad happens to it.
Then it will have an impact on the chain of custody as well.
Yeah, but at that point, you might just be worried about getting anything from the disk rather than... Because if you're really concerned about this, you can start bending the rules slightly, as life forensics tends to work. So the write blocker doesn't do anything. The flash controller destroys all this stuff. So it kind of looks bad, right? It looks like SSDs just destroy your data, you're screwed, you don't get anything back. But there's a flip side to this, oddly enough, in that actually trying to target evidence for deletion can be quite difficult. So Wei et al., which is the one I had something from earlier, I forget. They took 12 SSDs and some flash drives and a bunch of other stuff, and just sort of thought, hey, we'll try a bunch of crap out and we'll see what works. So they wrote identifiable patterns. So they just had patterns for each block or each page, and they would just increment it as they went along. So each pattern was identifying a unique part of memory. And later on, they would come back and physically pull all the NAND flash modules. Whereas the other two were using the software mechanisms, these guys actually looked at the low-level flash to see what's really going on with these devices. And this is where we found out that they do all this stuff like striping and compressing and generally making it a pain. So there are two erasure mechanisms. The first one is via your SATA ATA command. So you can actually send the command to a device which says, get rid of stuff. And the second one is software overwrites. So you can use DD and say, write for every address on the disk, put a 0 there, or put all zeros for the memory. So you just go back and you physically write over all the blocks. And they did it multiple times because they wanted to get the over provisioning accounted for as well. You can't access it directly, but if you keep writing to the disk, the wear leveling should eventually swap that memory in so it gets written over. So when you eventually pull it, that should be 0 as well. So they found that the ATA erase commands were unreliable. And this was mainly because the manufacturers hadn't implemented them properly or supported them at all. So even if they're part of the spec, it doesn't mean they've actually bothered to implement them. And they were basically useless. If you're going to wipe your disk, don't do it via one of these mechanisms. At least if you get any of these 12 drives. 2 overwrites of SSD using software mechanisms was found to be sufficient. So if I write zeros to my disk twice, that's basically the entire thing done. But there was a weird special case where they did this 20 times. So they did an SSD, they passed over it with zeros 20 times, and they still found 1% of the data when they pulled all these chips off. And again, that's just because the flash controller is the boss. You want me to write logical block 8000? No, I'm not going to do that. That page can sit there, I'll swap it in and out, but I won't do that. So all the swapping behind the scenes translation means that if you're trying to target something for deletion, you'll be quite lucky if you actually get it. And the worst thing, I think, was when they actually tried to target a single file or free space. So on a hard disk, if you say, I want to overwrite this file, you go and find out the clusters that it's been using on disk, and you say, 0 this, 0 this, 0 this. You know for sure it's gone because you know exactly where it lives. And then you also have to account for any other fragments that might be kicking about in the resident pages of the NTFS system. But you can't do that. You can't target particular hardware addresses because the flash controller is in the way. And for free space, where you would say, okay, all these clusters are not being used, let's write zeros over them. Again, you face the same problem. You don't actually have access to these physical addresses. So one more thing that was interesting is part of the write application thing I was mentioning earlier. When you're doing wear leveling, so if you're moving, if I write a block in one place and then I move it later because I want to erase that block, or I want to move it to somewhere else that is less used or more used, depending on how often the thing's been rewritten, you're generating all these copies, all this behind-the-scenes shuffling. If I have one file, I might have 16 copies of said file. And this graph represents, it's a histogram basically of the file copy counts. So you can see it sort of spiking up. So there's one file that's 16 copies, and it's quite frequent to have 6 to 12 copies kicking about on the actual disk. Again, this is actually hardware dependent, so you might find the algorithms are a bit better at dealing with the cascade of writes. But I think on the drives which are using more of the disks, you get 90% space used, you might find that you've still got a lot of this happening because it's struggling to keep up. So things overwrite themselves. You can overwrite a lot of it without doing anything, and if you try to overwrite something in particular, you're probably not going to get it. That seems just wrong. A few references. So these 3 papers are the ones I was talking about at the very end. I mentioned this earlier for the file system stuff, and these are 3 general purpose how SSDs work, SSDs for forensics, where you can find a lot of stuff I've talked about already. And I think that's it, unless any questions.
Survey papers on Stadia.
I don't know, there might be now, but I couldn't find anyone that quickly. I went on Forensics Focus, and they've got a wiki for this sort of stuff, and they didn't have anything substantially different to that. And when I had a look at it, I didn't even bother reading them because they didn't have any value. And there was a blog article posted in 2014 that said things are basically the same. So some of the earlier stuff was saying, oh, the future of forensics is pulling all these chips and doing all this stuff manually. Doesn't seem to have happened at all. It's played out quite a bit differently from how they expected, I think. Any other questions? Yeah?
Can we go back to the slide of the acquisition efforts, please? So there was a Red Walker JTAG.
Yes, it's just not,
That's fine.
I'm pressing the button and nothing happens because it's a Mac. Have I gone past it now? There it is.
So this might not be entirely relevant to what we talked about, but I'm just curious if you will answer. With the Red Walker method, in essence, what we're really doing is simply just mounting a hard disk drive, much like a USB stick, so you can browse any folder there. This is mounted correctly, you just cannot write to it.
Mm-hmm.
Yep. What I'm curious about is with the JTAG/debug method, what kind of data can we actually acquire from, say, a hard disk drive?
For a hard disk drive?
Yeah. Could we acquire the actual files of a hard disk drive from using the JTAG method, or is it more the operations?
I think you'll probably be looking at really low level stuff. What I probably should have mentioned is that the hard disks do a bit of this mapping as well. Not to the same extent, but you can have bad sectors, bad blocks on a hard disk, and that gets remapped. But it's not nearly the same level. So the firmware is the thing that's the boss on the hard disk. So when you're coming with the SATA interface, the firmware decides what to give you back, and if you get bad firmware that's been tampered with for anti-forensics reasons, you're going to have to do something maybe like JTAG, and I think that'll let you bypass it because you're not using the firmware, you're using physical properties of the board. So the firmware never actually boots up because you're entering this other mode of operation. And when you do that, I think you're probably able to get back like the rawest form of disk read, like what you would actually want from a physical acquisition using software.
I see, okay.
Never tried it though, but
I'm just curious, I don't know, so that's why I'm asking.
yeah. And one thing about the SSD stuff as well is if you're using JTAG, I'm fairly certain you can get individual NAND blocks back. Like if I've got 6 actual flash memory chips on there, I can say, okay, give me back this chip or give me back all chips, and I'm not worrying about the flash controller or any other layers of abstraction. But you know, I haven't actually tried it, so I don't know. I just know that this is a method of getting stuff off if you're really, really desperate and you find that software reads don't work very well.
Yeah, okay, fair enough, yeah.
Any other questions? No?